Hi, I'm Paul Durrant. Some of you know me, some of you probably don't. I've been working on the Zen project for about a decade now. I'm a senior principal software engineer at Citrix, working on the Citrix hypervisor product. This talk is going to be about QEMU, which we do use in Citrix hypervisor traditionally as the source of device models for emulation for HVM guests, but we're also using it now as the main PV storage backend for some of our storage repositories. And this is about some of the issues we ran into. So hopefully this is going to work. Right, this is a video of me running an HVM Debbie and Jesse guest. So while it's booting, we're going to go look at the config. And you can see it's got a disk configuration that has a QCOW2 in it, which means we're going to be using QEMU as our PV backend for this guest. So now it's booted, I'm going to go do something fairly innocent. I'm going to run ZenTop. Oops, what happened there? Something went wrong. And what actually happened was QEMU crashed. So there's a core file. Let's go have a look at the core file and see why it crashed. And it crashed because we hit an assertion failure, which is not very good, because we'd like to look at the storage backends through ZenTop, please. So why did we hit the assertion failure? So here's the assertion. It's in a function called block get attached device ID, or dev ID, sorry. And it's basically just trying to return some info about the block device, which is a pretty innocent thing to do, but you can see it has that assert at the top there. And the comment above the function mentions qdev ID or QOM path. What are those things? Well, let's have a start with qdev. qdev's pretty old. This is a slide I lifted from Marcus Armbruster's KVM forum presentation from 2010. So almost a decade old. It's pretty straightforward. It was QEMU's framework, or it is QEMU's framework for essentially providing a generic mechanism of exposing a device tree. So you have a tree of devices connected by buses. Once you've got this common framework, then you can have a common API to drive it. And a common mechanism of configuration and control. So fairly straightforward. Here's an example, again from the same slides. That's the sort of main PC architecture. So you can see we have system bus at the top, that then enumerates, or that's a device actually, then that enumerates, sorry, that's a bus, sorry. That enumerates various devices. You can see one of them's the i440 PICs there. So each bus is the child of a device. And then each device can then, in turn, enumerate more buses. And that's how we build up the tree. Nothing very surprising here. So let's move on to QOM. QOM stands for QEMU Object Model. This is content I lifted from Paolo Bonzini's 2014 KVM presentation, so a little bit newer. And essentially, it builds on what QDev started, essentially. It's a common framework for device creation, backend creation, every sort of object creation, essentially, and configuration in QEMU. And you can see here that serial device that's being added there has this ID, and that means that it fits into a name hierarchy machine peripheral serial 0. So the hierarchy is different from QEMU. It's different from QDev, sorry. It's not essentially expressing the topology. It's just providing you a canonical mechanism to name things. So let's go back to PV backends. Do they actually conform to QDev at all? Well, it turns out the answer is yes. Here's the Zen BE init function, which is called at start of day to initialize the backend framework. And you can see that at the top there, it's creating a sysdev device. That null there means that it's plugging into the main system bus. Then it creates a bus hanging off of that device. So, this is the basics of QDev. If we go look at the header file where those types are defined, you can see there's also a third type there, Zen backend. And that essentially means we have this hierarchy here. We have the main system bus, that enumerates Zen sysdev, that enumerates the bus, and that enumerates the backends. So let's see what we can do from a command line. Given these things, we should be able to configure them using the standard qdev commands on the command line, or via QMP, which is QEMU's configuration protocol, which is driven by JSON. So this is a command line. This tells us at least that the hierarchy is present, so it's not surprising it errors. I mean, I didn't create a machine, I didn't really do anything. All I did was start QEMU and tell it to enumerate a device, and it's just telling me that there's no bus to plug it into. So that's fair enough, the hierarchy's there. But when we go look at what we can do with the thing by adding the help option, not a lot, really. There's no way to configure the backend. There's no way to even tell QEMU what type of backend it is, whether it's disk or network or anything. So that doesn't seem particularly useful. When you compare it to something like the E1000 device model there, a whole bunch of parameters there. We can do all sorts of things, like we can tell it where to appear on the PCI bus. We can, give it an override its MAC address. We can do a lot of things with that. So how do backends get created? Well, it turns out that they're created essentially by open coding a whole bunch of stuff, which the QDev framework's supposed to do when it's configured properly. So you can see there we just go and gmalloc an object, tell it it's a backend, set up a whole bunch of stuff, plug it into a bus, and off we go, kind of thing. But where's the information come from? Well, the information comes from Zen Store. You can see this function here. That's called Zen Store Scan, so unsurprisingly it scans Zen Store. And whatever it finds in the Zen Store backend area, it will go and call that function over there to go and instantiate it as a Zen device, or a Zen backend device. And that's essentially why these things are legacy, because yes, they pay lip service to QDev and QAM, but they don't really use it properly. And that's a problem, because obviously we see ZenTop crashes as a result, and we weren't the only ones to notice this. This is from Kevin Wolf, who's one of the block maintainers in QEMU, and he also noticed that it was crashing and was basically at the point of sending patches to get rid of the PV storage backend out of QEMU, which is not good news for Zen Server or Citrix Hypervisor, because we were basically starting to use it in anger. So we kind of needed to do something. So how about we do something properly? Question is, what does it take to do things properly? Now, it so happened that I had some prototype code lying around where I'd started to think about this, so I rapidly got that off out of my repository and started to work on it to try and send it upstream. And this is what it ended up as. So it was an 18 patch series, and basically completely replaced the old framework with a new one that was actually properly compliant. So the first thing to do actually was to move the old code out of the way. Now this patch basically says, I looked at trying to do it incrementally in place. That just wasn't going to be practical. The way the old code worked, it was going to be really, really hard to pick it apart and then put it back together again properly without it becoming just one humongous patch. It was never going to be reviewable in that form. So I elected to move it sideways and then start again, essentially. So this was the patch that introduced the new hierarchy. You can see it basically has three things. It has Zen Bus, Zen Device, and Zen Bridge, and then this shows how they fit. So in place of the old names, we have the main system bus, but then we have the Zen Bridge device. Now that essentially does nothing other than create the Zen Bus, and then the Zen Bus enumerates the Zen devices. But that really doesn't look an awful lot different to what we had below. So we still have the problem about, well, how do we configure those things? How do we specialize them? Where are the parameters? Well, in QDev, there's a type hierarchy as well as the bus device topology hierarchy. So each device essentially has a parent type, which is called device state, and that's the basic QDev device. It does nothing other than exist, essentially. And then we can specialize these things. So I specialize the device state into a Zen device. And then later on in my series, I proceed and I specialize the Zen device into a Zen block device. And then I specialize Zen block device into two different things. So it's a Zen disk or a Zen CD-ROM. They have to be slightly different because of the way they handle pluggable media. So that's why there's two separate things. So now let's see what we can do from the command line. Well, firstly, you have to understand that QDev also has the concept of abstract types. Now, abstract types are sensible because when we want to instantiate a device, it's as it was before. It's meaningless to instantiate a Zen device because it's just a device. It doesn't do anything as such. But it's also because of that type hierarchy explaining the fact that CD-ROMs and disks are slightly different. It's also not meaningful to instantiate a Zen block device. So again, it's marked as abstract. But then we finally get down to the Zen disk device, and that is a concrete device, and we can instantiate it. So these options, whilst it says Zen disk options, are actually mostly inherited from Zen block because they're mostly common between the CD-ROM and disk implementations. So there's vdev, for instance, which is the place it appears inside the guest. So is it an XVD, an HD, an SD? And then there's things whether it's like shared read-writes, physical block size, logical block size, all the kind of things you'd expect. This one, however, is inherited from the Zen device, so the parent type of Zen block, because it's the front-end ID, and any Zen backend needs to know where its front-end is. So that's a common parameter as an example of something that's inherited down that specialization. So let's go look at this video now. Hopefully I can play. So we have our Jessie VM here again. This is booted. So we'll go look at what disk it's got plugged in. So it's just got the basic system disk. So let's find out what domain it is. And now I'm going to start up a QMP shell on the socket that libxl has already created. You can see we're running QEMU 4 here, which is the first version that had all the patches in it. And we're going to go and instantiate a secondary disk. So the first thing we need to do is tell QEMU what the image file is. So there's our disk qcow2 file. Then we need to tell QEMU that it's actually a qcow, so we have to tell it to interpret it as a qcow image. So that's what the second command is doing. And now we're going to go and create an actual Zen disk device to plug it into the guest. So here we go. It's XVDB plugged into the guest, and hey presto, there you go. It plugs in via the Zen bus protocol, and when we run fdisk in the guest, there it is. And similarly, we can go and unplug it again. So using standard QMP device del, we can go and get rid of it. There's its ID, off it goes. Run fdisk in the guest again, it's gone. And let's, just to be sure, plug it back in again, just to show this wasn't a one-off. Yep, there it goes, back again. And remove it again. And then just to be sure, let's run ZenTop, just to make sure it doesn't crash. Oh, look, QEMU didn't crash. So there we go. So problem is, what about the tool stack? Now, nothing I did changed anything about libxl. So libxl is still going to go and pile a whole load of stuff in Zen Store. And if we're only able to instantiate PV backends via QMP or the QEMU command line, then how are these things going to appear? Well, basically we have to have a compat layer. So each of the backend implementations can advertise one of these things, a backend create or destroy method, and then it can register it. The Zen bus code will scan Zen Store in the way that the old code did, but what it will do is for everything it finds, it will look up to see whether it's got a create destroy pair for that. And it's looking up using this name, which is the name it will find in Zen Store for the backend type. So in action, we can see this. So that's that Zen Store stuff. What ZenBus will do is it will wrap up whatever it finds in Zen Store into a dictionary of options, and then it will call the create method. Now, it's that create method's job essentially to fake QMP. So that create method in Zen block will actually call QMP block dev add. So that's like I'm typing that on that QMP shell. Similarly, it can add parameters for that Zen block. So one of the parameters that Zen block supports is IO threads. So again, it will do a QMP instantiation for an IO thread. The only thing it doesn't quite go in at the QMP layer for is the qdev creation itself, because it was more complex than really needs be. Creating qdevs is fairly simple, and there was no need to actually really go to the expense of wrapping stuff up, passing it to the QMP layer, only to have it unpack everything and create the device. So let's just go and have a look in the log. So this is the system disk and the CD-ROM for that Jessie VM. So I brought the guest up paused, and we can go and see what QEMU is doing. So we can see that ZenBus has identified that it's got a type QDisk there. That's its path. It then calls into that ZenBlock create method. That ZenBlock create method is now going and magically instantiating HDAQCow2, realizing the device, that's the QDev creation part of it, and it's now ready with the front end and the back end in the appropriate states for the front end area and the back end area in ZenStore in the appropriate states for the front end driver in the guest to start. Similarly, it does the same for the CD-ROM there. And then you can see at the bottom, it's also found a back end for console. Now, I don't have a PV console front end in my guest, so that's actually not going to go anywhere. But you can see it will work generically. So actually, I've already said all this. So next steps. ZenBlock is the only thing that's been transferred at the moment. So the next step is to make the other backends into new devices. So get them out of that legacy framework. So eventually we can retire the legacy framework. And then the other obvious thing to do is to teach libxl how to talk QMP directly rather than having to go through that Zen Store dance, and then we can get rid of that compat code. So that's the end of the talk, and I'll take questions. Oh, back there.
Does this lend itself to separating out maybe your disk backend from maybe some of the other backends that are running, so you can have separate processes that did each one?
I mean, you could spin out the code separately from QEMU completely, more or less. I mean, it doesn't use any of the QEMU sort of facilities, really. The PV backends have always been slightly separate. So yeah, it would be perfectly feasible to lift that code sideways into its own thing. I mean, QEMU itself is not really buildable in such a configurable fashion, but there's, I think, pressure from quite a lot of sources to make QEMU do that. So with any luck, maybe we'll start to see a proper kconfig style breakdown, so we can build just the PV backends. I mean, in Zen Server or Citrix Hypervisor, we actually do that. We've hacked QEMU. Well, rusted it actually, to hack QEMU so we can build just the PV parts of it to get the binary image down to a manageable size, because if you build all of QEMU, yes, it's quite big. Okay, I think that's it. Thank you.